Hello, welcome to my video series of algorithms. This is part 10 of Module 1, Sorting Algorithms. In this video, we will discuss the Radix sort algorithm. In the previous video, we learned the bucket sort algorithm. We know that it has a time complexity of O(n plus k), where n is the number of input elements and k is the number of key information categories. We demonstrated the potential problem of sorting large numbers with bucket sort. Recall that if we directly map a real number into a category, a large number like 999,999 would mean k equals to 999,999, which could cause potential problems in both efficiency and space consumption. Therefore, we will want to address this issue and extend the application of bucket sort to large numbers. Meanwhile, we also analyzed that the best use case of the bucket sort algorithm is when n is much larger than k. An application that satisfies the condition is when sorting strings. In this case, k, the number of buckets we have, equals to the alphabet size of the strings. We will see that these two problems are conceptually the same when we break the numbers into digits and the strings into characters, where these atomic elements are referred to as the radixes. By sorting these radixes with the Radix sort algorithm, we can solve both problems efficiently. Let's see how we can unify the number sorting problem and the string sorting problem by breaking down the input elements into radixes. First, a number is composed of digits. N can be represented as a string comprised with the characters representing these digits. For example, the number 324 can be represented as a string of 324, where the first character is 3, the second character is 2, and the third character is 4. Note the ordering of the digits is the same as the lexicographical ordering of their corresponding characters. For example, the digit 1 is smaller than 3, and the character 1 is also lexicographically smaller than the character 3. However, the lexicographical ordering of strings could be different from the ordering based on the numerical values. For example, the number 23 should be smaller than 145. But the string 23 is lexicographically larger than the string 145. It is because its first character 2 is lexicographically larger than the first character 1 of the other string. Note that the difference is that number comparison is right-adjusted, where the comparison between elements with different numbers of digits should align their rightmost radix. On the other hand, string comparison is left-adjusted. To unify these two sorting problems, we will pad null characters to make the numbers and strings to be sorted equal in length. We will pad zeros to the left of the numbers and pad $signs to the right of the strings. The null digits or characters should rank before all other digits or characters. With the padding, the ranking of the values among numbers will be the same as the lexicographical order among strings. For example, when sorting numbers 23 and 145, we first make strings 23 and 145, then pad 23 into 023. Now, the lexicographical ordering of strings 023 and 145 is the same as the ordering of numbers 23 and 145. For string sorting, consider the ranking of strings learn and algorithm. We cannot pad $sign at the beginning of the string learn, as that would rank $learn before algorithm. We pad at the end, in which case the string algorithm will rank before learn $. Now, since we have shown how to solve the number sorting problem using string sorting, we will focus on solving the string sorting problem. We will demonstrate the idea of Radix sort with the following toy example, where we are sorting strings Google, Gi, the, good, gold, and goose. First, we pad them with the null characters $sign. Note that when implementing the algorithm, we don't need to explicitly pad the characters. We can simply infer the padding by checking whether the index is out of bound. Intuitively, at this point, we can begin by comparing the first characters from the strings, rearranging them, and then comparing the second character from the strings, rearranging them, and so on. For the sorting based on characters from a given position, we refer it as a sorting phase. The above approach is called the most significant digit first radix sort, or MSDF radix sort. Alternatively, we can sort in the reverse way. We can begin by looking at the last character, the second last character, all the way through the first character. This approach is called the least significant digit first radix sort, or LSDF radix sort. Both approaches will yield correct results. However, the less intuitive LSDF radix sort is actually more efficient. As a result, we will focus on the LSDF approach in this video and cover the MSDF approach in the next video. Okay, let's go back to the example. With the LSDF scheme, we will first sort the strings based on the last characters. We will use bucket sort for this purpose. This is because in this case, the number of buckets we have is the same as the alphabet size. For example, when we are sorting English strings, the alphabet size will be 26, and when we are sorting ASCII strings, the alphabet size will be 256. In this case, we will have the number of buckets k as a constant, and the bucket sort algorithm will run very efficiently. With bucket sort, we will sort the strings based on the last character in the first pass. The sorted positions are colored black. Then, we look at the second last position, which is colored red here. Here is the result after the second pass of sorting. The third pass, the fourth pass, the fifth pass, and finally the sixth pass. You can verify that after sorting all positions, the strings are lexicographically sorted. Now, let's write the pseudocode for the LSDF radix sort algorithm. We first define two functions. The first one is the bucket sort function. It takes three parameters: the input array A, output array O, and the number of key information categories, K. Each entry of the input array A contains two fields, the data field and the key information field. For example, recall the student record information introduced in a previous video. We have tuples like student ID, grade, such as 000A and 001C. Here, the student ID field is the data field, and the grade field is the key information field. We further define the second function, makeKey, which takes in parameters a, x, and I. The function assigns x to the key field of AI. Here is the pseudocode for the LSDF radix sort algorithm. In the inner for loop between lines 5 to 7, we define the key information as characters from different positions of the strings. In line 8, we call the bucket sort function. And in line 9, we assign the output array as the input for the next sorting phase. Now, let's analyze the correctness of the algorithm. While it is obvious that the MSDF radix sort is correct, as the procedure directly implements the sorting criteria, it is less obvious why the LSDF radix sort is also correct. The key to seeing the correctness is to recognize that the bucket sort algorithm is a stable sorting algorithm. Recall that by stable sorting, we mean that the relative orders of the equal elements are the same as their relative orders in the input. Note that based on the radix sort algorithm, the input of the current phase is the output of the previous phase. Therefore, when discussing the radix sort algorithm, we say that the relative orders of the strings that share the same ith character are the same as their relative orders when sorted by the I+1th character. For example, consider the third and the fourth sorting phases of the example. In the right matrix, the three underlined suffixes are sorted together in the fourth sorting phase, as all of them begin with the character O. Note that their relative orders are the same as those in the left matrix, which is resulted from the third sorting phase. To generalize, consider the result generated after sorting the ith position. Based on the correctness of the bucket sort, we know that elements with different characters in the ith position will be sorted correctly. In addition, we are also interested in seeing whether the elements with the same character in the ith position are also properly sorted. Based on the stability of bucket sort, we know that their relative orders are the same as those sorted based on the I+1th position. If the characters at the I+1th position are different, then their orders have already been resolved when sorting the I+1th position. Otherwise, we can look into the phase that sorts the I+2th position, and so on. We know that either at some position, all ties will be broken, or the characters are still identical until we reach the last position. In the second case, all suffixes starting from the ith position are identical, and their relative orders do not matter. In either case, all suffixes starting from the ith position are properly sorted. When I is set to 1, the entire set of strings is properly sorted. Therefore, the LSDF Radix sort is correct. For time complexity, recall that the bucket sort algorithm runs in O(m) plus k time. Also, define W as the maximum length of the input strings. In this case, the algorithm needs W sorting phases. The total time complexity becomes OW times n plus k. For the space complexity, recall that the bucket sort algorithm needs O(m) plus k space. However, we can reuse the same buckets for different sorting phases. So, we only need k space to hold the buckets throughout the entire algorithm. In addition, we also need OW times n space to hold the strings. Taken together, the space complexity is OW times n plus k. In summary, we have discussed the LSDF Radix sort algorithm in this video. The algorithm extends the bucket sort to allow its application in general number sorting and string sorting. Its time complexity is OW times n plus k, and the space complexity is OW times n plus k. In the next video, we will discuss the MSDF Radix sort algorithm. Thank you for watching, and see you next time.